Thank you, everyone. Thanks to MCQST for putting this wonderful meeting together. Very broad, very interesting. So this is the session on quantum matter, and the first of the four speakers. So the work that I'm going to talk about was really spearheaded by a wonderful graduate student of mine at MIT. His name is Ethan Lake. And it was done in collaboration with Mike Hermele, who's a faculty member in Boulder. So a paradigmatic model in quantum matter is what's known as the Bose Hubbard model, probably familiar to the portion of the audience that works on condensed matter physics, cold atoms physics. So the Bose Hubbard model was introduced in this paper a long time back, and it captures the competition between boson kinetic energy and interactions when the bosons move on a lattice. So there's a hopping term for the bosons. The bosons are allowed to hop from one side to the other on a lattice. There's a chemical potential term that tunes the density of bosons on the lattice. And there's a boson repulsive energy, or an energy cost for having multiple bosons sit at the same lattice site that describes the interactions between the bosons. So there's many beautiful experiments in cold atom systems that have been done on this model, all of which were pioneered right out here in Munich by the people who now lead the MCQST. So it seemed appropriate to talk about some variation on this Bose Hubbard model at this meeting. So let me start right away by talking about some important symmetries of the Bose Hubbard model. First, there's the conservation of particle number. So the particles can move around, but the total numbers are preserved by the dynamics of the model. So we'll call that a global U1 symmetry. That's theoretical physics speak for saying that particle number is conserved. And there's a symmetry of lattice translations. Every lattice site is the same as every other lattice site. And these will be the important symmetries to the model. And the phase diagram, the ground state phase diagram, what the model does at zero temperature, can be organized by asking whether these global symmetries are preserved or whether they're spontaneously broken. Okay? So here's the famous phase diagram of the Bose Hubbard model described in this old paper. So on the vertical axis is the ratio of the chemical potential to the interaction energy. On the horizontal axis is the ratio of the boson hopping to the interaction energy. Now, MI stands for Mott insulator. So this is a phase in which there's a fixed number of particles per lattice site. That's the physical picture one has of this phase. And the bosons are not able to move around at low energies through the lattice, so it's an insulator. And this Mott insulator, so these different labels, n equals 1, 2, and 3, describe the occupation number of each lattice site. You can have a Mott insulator where there's exactly one particle per site, or an insulator where there's two particles per site, and so on and so forth. And this Mott insulator preserves all the symmetries of the Hamiltonian of the Bose Hubbard model. Okay? Now, as you increase, sitting in the Mott insulator phase, if you either increase the hopping or you sit somewhere here and you change the chemical potential away to change the charge density of the model, you enter into a superfluid phase where the bosons are mobile and they form a superfluid. Okay? So this is an iconic picture that was created by Emmanuel Bloch 20 years back that describes the superfluid insulator transition in an optical lattice using rubidium atoms. So here's the Bose condensate, the peaks in the momentum distribution. And in the Mott insulator, you just see some uniform distribution in K-space. So the superfluid phase has a close relationship with the phenomenon of Bose-Einstein condensation. In fact, the relationship is so close that even the very language that we use to describe the superfluid phase, we often interchangeably say superfluid or Bose-Einstein condensate, right? So it's in textbooks, it's how I speak myself. But they are somewhat different phenomena. And the superfluidity refers to the existence of a non-zero phase stiffness in the model in this ground state. Phase stiffness means that if you test the system by turning on an external static vector potential that couples the boson currents, then the ground state energy density changes as a function of this static vector potential by some constant times the square of the vector potential. Okay? And the coefficient is the phase stiffness. And so long as the phase stiffness is 0, one would call the system a superfluid. Okay? Now, the ground state also has spontaneous breaking of the global U1 symmetry. There's an expectation value for the boson destruction operator at each site that is uniform in space. And this symmetry breaking implies that this correlation function is non-zero for large separation between r and r prime. And if you're taking the Fourier transform of this equation, you'll conclude that the momentum distribution function has the delta function piece at zero momentum, which is basically telling you that the zero momentum state is macroscopically occupied, and that's the phenomenon of Bose-Einstein condensation. Okay? But these two go hand in hand, so there's a mantra that's developed which says that superfluid is the same as Bose-Einstein condensation, or equivalently spontaneous breaking of this global U1 symmetry. So the superfluid, if you're not interested in the short distance details and you just want to understand universal long distance properties, you can ask what the universal long distance properties are. And at long distances, the excitations of the superfluid are sound waves. And these sound waves can equivalently be thought of as Goldstone fluctuations associated with the broken symmetry. So it's just the fluctuations of the phase theta of the boson. And the equation of motion is just the equation of sound. Or equivalently, if you prefer to write a Lagrangian, then you write some such quadratic Lagrangian for these Goldstone fluctuations. And this coefficient in front of the time derivative term is a thermodynamic quantity. It's the compressibility of the system, while the coefficient in front of the spatial gradient term is what is the phase stiffness that I already introduced. So you can use this long wavelength theory to discuss the low temperature thermodynamics, the low temperature dynamics, the stability to thermal fluctuations, to quantum fluctuations, and so on and so forth. So all that is a known story. It's in textbooks that have been studied in experiments in detail. So what I'm going to talk about is a modification of this paradigmatic model, which turns out to have a lot of fascinating properties. So I'm going to modify the model by including another global symmetry, and that's a symmetry that I would call, apart from the conservation of particle number and lattice translations, I would call that symmetry a conservation of dipole moment. So the dipole moment, for my purposes, I'm just going to define it as this operator. It's this, so the particle number is just sum over r and r, while this dipole moment is a vector, it's sum over r, the vector r times nr. Okay? So in d dimensions, there are d symmetries associated with the dipole moment. So we can ask about the ground state phase diagram, and we can ask about whether the ordinary global U1 symmetry and the new dipolar symmetries are preserved or whether they are spontaneously broken. So this dipole preserving dynamics means that a single boson can't just move. That will violate the conservation of dipole moment. But two bosons can push off each other and move in opposite directions or move sideways and so on. So this hop is forbidden. Well, if you have a pair of bosons, this yellow hop is allowed or this blue hop is allowed, right? So that's the kind of dynamics that we are contemplating for the bosons in this model. So what's the context? Why am I interested in such a modification? First, there's a lot of beautiful work coming out of MCQST on models with this kind of dynamics, right? So the focus so far in most of the work has been on the dynamics, on how the system evolves in time, because in the presence of such dipolar symmetries, it turns out there's all kinds of interesting kinetic constraints which affect things like thermalization and so on and so forth that come from dipole conservation. So it's a nice and important theory from Frank Pullman and his group, some of whom are probably in the room, and also by others. And this experiment also by the Eidelsberger lab. Again, many of the group members are probably here. And by the Wasim Barker lab at Princeton. Now, there's a natural realization of dynamics that conserves dipole moment, at least in some parameter ranges, if you take an optical lattice and strongly tilt it, right? And that's what was used in these experiments. So if you imagine strongly tilting an optical lattice, and say you have a particle here, it can't hop to neighboring sites without changing its energy, right? So that's forbidden. But if you have a pair of particles, then maybe one particle can go up in energy, the other particle can go up in energy, and you get dynamics that preserves the dipole moment. Okay? So there is a realization of this kind of dynamics in the cold atom setting. Now, there's also interesting connections with formal work, both in condensed matter physics and in quantum field theory, where people have imposed some sort of dipolar symmetry to gain insights on exotic topological matter or in exotic quantum field theories with a lot of benefit. Right? So there's a lot of good reasons to think about symmetries that preserve dipole conservation. So I'm going to study this dipolar Bose Hubbard model. So compared to the usual Bose Hubbard model, all we want to do is to modify the hopping term so that we conserve the dipole moment. So the hopping term should allow, for instance, a pair of bosons to hop so that one of them goes here, the other goes here, or for a pair of bosons to be such that, again, one of them goes here and the other comes here, right? So that's captured by a term of this sort. And the other terms in the Hamiltonian are the same as before, right? So that's the model that I'm going to think about, okay? So it changes the phase diagram dramatically compared to this iconic Bose Hubbard model. So it's the same axis, mu over u, versus this dipolar hopping term, T over u. So I'll mainly focus on the new things in the phase diagram. There are two new phases that are particularly interesting. So DC is what I'll call a dipolar condensate. And most interesting is this blue phase called BEI, which is what I'll call a Bose-Einstein insulator. Okay? So let's start with the Mott insulator. The Mott insulator occurs in the limit of weak boson dynamics, weak boson hopping, or in this even this modified hopping. So in this log U limit with integer number of particles per site, there's almost no difference from the standard Bose Hubbard model, and you just get the usual bosonic Mott insulator as in the standard model, right? So each particle just sits in one of the in the minimum of the potential. Okay, so let's stay at integer filling and let's increase this modified hopping term. Now, single bosons cannot hop, but these dipoles can hop, right? So you can have the yellow hops or the blue hops. So more formally, if you think about this dipole creation operator, where you destroy a particle at site I and create it at site I plus A, and we'll call that the dipole creation operator. So this has the usual hopping dynamics, right? So with increasing T, these dipoles will lower their kinetic energy, and at some point, you'll overcome the gap that's there, starting from the Mott insulator, the gap for creating these dipoles, and eventually, these dipoles will condense, and you'll get the dipolar condensate, right? Now, whether all the dipoles condense, the dipoles in different directions, or only some of them condense, depends on details of the model. So in the simplest case is to consider a situation in which the dipoles in all the directions condense and have non-zero expectation values. So let's play the same game that I described for the usual superfluid. What about the long wavelength fluctuations? So here it's much more useful to take this perspective of Goldstone physics. So you're breaking all these symmetries associated with dipole conservation, and correspondingly, there are d Goldstone modes parameterized by phases phi a of the different dA operators. Okay, so phi a is a vector with d components. So really, the phase fluctuations of the dipolar condensate are a gapless vector field, a field that transforms as a vector under spatial rotations. So it has some corresponding Lagrangian, which has time derivative terms and various kinds of spatial gradient terms. Okay? So that's the description of this phase DC. Now, the single bosons continue to be gapped in this phase. I start from the Mott insulator, increase T over U, I end up with this dipolar condensate. And so this phase continues to be an incompressible Mott insulator. You can't add particles to the phase, but you can add dipoles, right? Which doesn't change the particle number. Okay, but now let's ask about what the bosons are doing in this dipolar condensate. So once I spontaneously break the dipole symmetry, that liberates the bosons from, earlier the bosons couldn't move by themselves, but the dipole condensation liberates the boson hopping and allows the bosons to get some kinetic energy. So one way to think about it physically is that single bosons can now move by absorbing or emitting dipoles into the condensate. If you prefer equations, then you start with something like this, and having an expectation value for the dipole operator simply means that you can factorize this way, and this is just some C number, so then you have boson hopping. Okay? So now, as you increase T over U further, or you dope away from integer filling, given that the bosons can hop in this dipole condensate, you expect that the bosons can then condense once you once they start being able to move, right? So single bosons you expect will condense, and that there'll be a phase transition to this new phase, which I'm calling the Bose-Einstein insulator. As we'll see, this Bose-Einstein insulator is a fascinating phase. It's a compressible phase of matter, but it's insulating, okay? And we'll see that it often has an actual Bose-Einstein condensate as well. Okay, so let's ask about the long wavelength theory of this Bose-Einstein insulator, this phase where single bosons have condensed. So as I said, you can factorize this hopping by taking an expectation value of this dipole operator in the dipole condensate. Now, replacing this expectation value with a magnitude and a phase. The magnitude is the order parameter for this dipole condensate, and the phase is this Goldstone mode of the dipole condensate. We see that this phase couples to the boson hopping as a spatial component of a gauge field. Okay? Just the spatial component. So when the boson is condensed, you must include the phase of the boson itself, along with this vector phi in the long wavelength theory. And given that this vector phi couples the boson hopping as a spatial gauge field, what earlier in the standard Bose superfluid used to be just a gradient theta squared term, now becomes a gradient theta minus phi squared term. This is pretty much like what you may recognize as a Meissner effect in a superconductor or the Higgs mechanism in particle physics. So the fluctuations of this field phi then get gapped. You can simply shift phi by gradient theta, and that gives a gap to these fluctuations. Now, pursuing this further, I won't describe it fully, but it's just a couple of lines. There's an effect of phase-only Lagrangian that describes the long wavelength fluctuations of this Bose-Einstein insulator, and it looks very similar to the long wavelength phase action for a superfluid. So that's the time derivative term, just as before. Sorry, this is a typo. This should have been theta. But the spatial gradient term, instead of gradient theta squared, you now have gradient squared theta squared. Right? So that's the only modification compared to the usual story. And this model is actually well known from the literature. It shows up in other contexts. It's what's called the quantum Lifshitz model. But here it shows up very naturally. So we can use this, just as we do for the superfluid, to address the stability of the Bose condensation in various dimensions. You can do it at 0 temperature or at finite temperature. I'm just showing the answers for 0 temperature. The main question one wants to ask whether these long wavelength fluctuations destabilize the Bose condensation. Okay? So the standard way to approach such a question is to calculate this expectation value within the Gaussian long wavelength theory. So you can do that. And the answer is that in 3 dimensions, the Bose condensation is stable. In 2 dimensions, you get quasi-long-range power law order. And in 1 dimension, you just get short-range order. Okay? Okay. So I said I've been calling this the Bose-Einstein insulator. So now let me explain why it's insulating in any dimension. So know whether it's a superfluid or an insulator, we should turn on a transverse vector potential A and look at the response of the system to this vector potential, right? Just like we did in the superfluid. Again, I've inherited the same typo. So this Lagrangian that describes the long wavelength fluctuations gets modified in the presence of such a vector potential. The gradient theta is shifted to gradient theta minus A. But now, because I take a divergence of this whole thing, so long as my vector potential is transverse, divergence A is 0, and there's no coupling to the transverse vector potential. This means that this model has no phase stiffness, despite having a Bose condensate, and there's no conductivity. It's insulating. Okay? But the response to a scalar potential is 0, this term. As I said, the coefficient of this term is the compressibility of the phase. So this phase is compressible, but it's insulating. Right? It's not a superfluid, it's an insulator. It's the other extreme. So what's going on? Right? It seems like what I said is more or less the standard mantra in all textbooks seems to have been violated. So what's going on? A rough understanding from a physical point of view of what's going on is in this slide. So the dipolar symmetry makes it completely natural that you will not get superfluidity. Okay? And the reason, again, there's a two-line proof, but I won't give that explicitly here. You can use the dipolar symmetry to show that the current, the particle current at 0 momentum, so it's a uniform current, that operator is exactly 0 in any state in the system. So there's no question of this system being in a superfluid phase or even in a metallic phase. In fact, you can show that the conductivity is 0 at all frequencies. Okay? So maybe that's not a surprise. So what's a bit more of a surprise is how to reconcile that with the spontaneously broken global U1 symmetry, which is stable as long-range order, at least in 3 spatial dimensions. Okay? So what happens is that because of this dipolar symmetry, the way the dipolar symmetry acts on the boson operator is such that a condensate at 0 momentum is in fact degenerate with a condensate at any non-zero momentum. Right? You can shift the momentum of the condensate through a symmetry action, this dipolar symmetry, without paying any energy cost. So in fact, the system has a highly degenerate ground state. Depending on your taste, you can pick the ground state to be a Bose condensation at 0 momentum or at any non-zero momentum. And these are all part of the manifold of ordered states about which the system is trying to fluctuate. So this is an extremely unusual BEC. Sure, it spontaneously breaks the global U1 symmetry, but it's a very weird kind of BEC. And this weird BEC, quite naturally, you might imagine that it has weird fluctuations which prevents the superfluid response. Okay, I'm almost at the end. So there's a lot more that you can do in terms of analysis of this model. You can study the phase transitions. You can consider various variants. Now, there's a particular variant that is natural in a tilted lattice realization. Typically, you can only tilt the lattice along one direction. So then you might imagine that the more appropriate model is one in which dipole moments along some direction are conserved, but not along other directions. And you can analyze it pretty much in the same way as I've described in the main part of the talk. But you get even more unusual phases. For instance, I'll draw attention that there's the Mott insulator and various other phases. I'll draw attention to this phase. It's some sort of anisotropic superfluid. And what it is it's a superfluid in one direction, and it's an insulator in the other direction. Right? Again, this is not something that can happen in the absence of this dipolar symmetry. So let me stop here. So imposing these extra symmetries changes the phase diagram of the usual Bose Hubbard model in some dramatic way. So I mainly focused on this Bose-Einstein insulator, which is a state of matter which has a global U1 symmetry, which breaks the global U1 symmetry spontaneously, but the corresponding current does not have any superfluid response. Right? This questions the general validity of this mantra that superfluidity is the same as Bose-Einstein condensation. Right? So clearly it isn't. Right? And so I've imposed dipole symmetry microscopically in the model that I've studied. But it's possible to consider situations in which I don't impose it microscopically, and it just emerges as a low-energy symmetry in some special point of the phase diagram. And there are situations where that happens, and in those situations, once again, this equation is violated. Right? So I think it's generally true that in many situations, superfluidity and Bose-Einstein condensation are the same phenomenon, but it's not always true that they are the same phenomenon. So this natural realization of a strongly tilted optical lattice has approximate dipole symmetric dynamics up to a very long scale, very long time scale. And that's what people have exploited, Beidelsberger and Wasim Barker, to study the effects of this dynamics on the time evolution of the quantum many-body system. Now, there is a catch to doing this in a tilted lattice. The strength of the dipolar hopping term cannot become very big, at least in current realizations. Right? Now, all the interesting stuff that I've talked about occurs specifically when the strength of the dipolar hopping term becomes big enough. So there's a question of whether these some new ideas needed on the experimental front to be able to tune these to this large dipole hopping limit. So with that, let me stop. Thank you.
Thank you, Senthil, for this very nice talk. Are there any questions? Maybe I can start with a question. So as an experimentalist, I was wondering what would be a good solid-state system to implement this Bose-Einstein insulator? Do you
it's probably very hard in solid-state.
Okay.
At least not with microscopic dipolar conservation symmetry. You can get this emergent dipolar symmetry. And there are examples where if you have a superconductor that's undergoing a phase transition from ordinary zero momentum superconductivity to non-zero momentum superconductivity, so-called FFLO phase, then that critical point has this emergent dipolar symmetry. And you can, in 3 dimensions, so at such a transition, you would have Bose-Einstein condensation, but not superconductivity.
Mm-hmm. All right, thank you. Are there any other questions? Yes, over there. Is there a microphone? Okay, I will give you mine.
Yeah, thanks for the nice talk. I was wondering if you could put a number on like how strong the dipolar hopping term has to be in, let's say, units of on-site interaction strength before you start to see the dipolar condensate and also the BEI phase. And then maybe following up on that, like how large is that that dipolar condensate phase?
Yeah, so we don't have a quantitative study yet that's in the works. My student is in the, you have to do numerical calculations for that, right? But the issue that I raised in this very last point is a parametric issue. So you need this dipolar hopping to be of order U or bigger to see these phases. You're asking about the precise number, but parametrically, it at least has to be order U or bigger, right? Now, when you generate it in a tilted lattice, you can argue that it's parametrically smaller than U, right? So there's if you call V the slope of the tilted potential, then the hopping that you generate is U times some number that's the ratio of the single boson hopping divided by this V squared. So it's parametrically smaller. So there's some new idea that's needed to, it's not as simple as just tilting the lattice. You have to do something else.
Thank you.
Hello. So one question about, so you have this ground state degeneracy at the different momenta. So would you expect, so this is on the level of Gaussian fluctuations, would you also expect that there's some order by disorder type of lifting of this degeneracy if you go, for example, to include the fluctuations beyond the Gaussian ones? Yeah,
so you can handle all that within the framework of this theory. Yeah, so the nonlinear terms are also severely restricted by the dipolar symmetry, right? So for instance, I can't just add a gradient phi to the 4 term or things like that. And so this quadratic analysis that I did is actually sufficient. And you can address finite thermal fluctuations all within the same framework.
Okay, good thing. And do you expect any interesting Kosterlitz-Dowlitz finite temperature for the superfluid because of the coupling to the dipolar condensate?
No, there's no superfluid here, right? You meant the Bose-Einstein?
Yeah.
Yeah, so there is a finite temperature phase transition in 3 dimensions that's associated with the proliferation of vortex lines, but it's 3D, so it's not Kosterlitz-Dowlitz. The transition is in the universality class of the 3D XY model, but inverted.
Okay, good, thanks.